Yeah, it like thinks that there's green screens. Cool. How do you? Got it. All right, is the camera going? It's managed to catch all of my confusion. Cool. All right. Well, finally, after one high-level lecture and one kind of lecture full of background stuff, we're going to go into material which is unambiguously geometric. In particular, today we'll be talking about the theory, both continuous and discrete, for understanding curves. And this shows up in your homework if you haven't looked at it. So if you need more motivation to learn about it, then perhaps that does it for you. Before we get started, are there any questions about either the homework, the course project, any of that? No? Okay. Cool. You should start the homework. Cool? Like, I'll be really generous with helping you with it, but I can't if you haven't even looked at it. That's going to be our agreement here. Cool. So, my question for you to start out with is a pretty simple one, right? I think we all use the word curve and more or less know what it means, but mathematically, my question is, what is the curve, right? And I think it's easy to overlook this problem and think about it like, you know, obviously when we kind of a squiggly thing or maybe a function, whatever. You know, we think about this a lot in calculus class, even like maybe middle school algebra class, we've seen curves before. But really stepping back and thinking about it from a geometric perspective, I think is valuable and worth calling out myself before going into the differential geometry, which you might not know. So remember that what I care about is that a curve is a geometric object, right? Like this purple line here. And probably our intuition, for example, from algebra class, is that a curve has something to do with a function, right? Like I have some function f of x which go, or f of t, maybe t is time, and for every t I assign a position on the plane, or 3D. And maybe that's a reasonable definition of a curve for you know, about 82% of your purposes. But for us, it's actually not quite good enough. In particular, there's one counter example, which I think you could all cook up, but maybe like doesn't come to your head immediately when I ask you, what is a curve? And that's this one here, which is, let's say that I made a function, gamma of t here, and I don't know why gamma 3, but whatever. And it maps every single time t to the origin. I think most of us would agree that this is a point. But somehow, somehow what this is, even though it's a kind of goofy counterexample, is an indicator that the simple definition of a curve as a function from time into 2D or 3D space is just not quite sufficient. Right? And so we need to be a little more careful about that. And in fact, if we really dig into, you know, being evil math counterexample people, we can come up with all kinds of reasons why this particular definition doesn't make any sense. Right. In fact, there's a whole series of books called Counterexamples and Analysis, which are so much fun to read. Essentially, there's some mathematicians that don't want to prove stuff, but just want to prove you wrong. Right? And they have beautiful examples. But anyway, in geometry, another example that maybe comes to mind is this kind of weirdly complicated function f2 here. Right? So my question is, I have two different functions, f1 and f2. Right? So f1 goes from t to, you know, t comma 2t as a couple. And f2 does that until t reaches time 1. And then when at time 1, all of a sudden, you replace it with some other function of t. Yeah? But if you plot these things, like you look at their trace on the plane, what you notice is they're both actually the same. Right? They're both the same curve. Right? So even though these are two different functions, effectively what f2 is doing is I get to time 1, and all of a sudden, like I see the police behind me, I jam on the accelerator, and I zip across this curve faster. But it's still the same curve. Right? As a geometric object, it's still a line in the plane. I know this is pedantic, but I think it's worth kind of calling out all of these different exceptional cases to make you realize that when we talk about geometry, we're really worried about the trace that this object makes in this case in Euclidean space, rather than the function f of t. And that there are some things that you can calculate on f of t, and some things that you can look at as kind of a point set, and they're not necessarily going to end up being the same conclusions that you draw. Right? Yet another, continuing our gallery of bizarre things, maybe if I say specifically I want a smooth curve, and then I say, oh, well in that case, maybe a smooth curve is a smooth function f of t, right? And it turns out that doesn't work either. And so here I give you an example. This is f of t goes to t squared and t cubed, and it essentially hits what we call a cusp, right? And the question you might ask is, well, okay, so individually the x and y components here are smooth functions of time. That's certainly true. So what went wrong is essentially, if you think of this as like a car driving along the curve, right, at t is time, the car comes to a full stop, you know, pivots around about 90 degrees, well, 180 degrees, and then keeps driving. right? But because he came to that full stop and then smoothly turned and then kept moving, this is a smooth trace, even though the geometric object he made in the plane was not smooth. Yep. So these are the sorts of things that, if you open a differential geometry book, you open DeCarmo and you look at page 1, this is the kind of stuff that you have to worry about, right? That somehow our intuition from calculus class isn't quite enough to get us to understanding the geometric object underneath the function f. I won't deny that having a function, a parameterization like f of t, is useful for a lot of calculations, but it's not the end of the story. Yeah. So, yes?
Does the curve have like this notion of direction? Or,
Yeah, in this case, this curve is oriented, right? There's a notion of t plus. But I would argue that as a geometric object, at least a basic curve, probably doesn't have that. We'll return to that actually a little, right at the end of lecture if we have time. Right, so if I'm talking about the geometry of a curve, then really a curve is a set of points, right? It's not a function, it's a set of points in the plane that traces out a curve-like object. And so this is what we have to figure out, is what is the proper definition here? So hopefully this is a reasonable motivation. And typically, actually, our motivation is quite close to the beginning of the calculus story, but then we diverge a little bit, right? So to me, a line, or a curve rather, is an object where if I zoom in close enough, right? I take my iPhone and I take my fingers and push them out far enough, and I keep looking closer to the curve. Eventually, it looks like a straight line. It looks like a one-dimensional object. Now remember our quiz question, right? No matter how close I zoom into a graph where I have a vertex of degree 3, it always looks like a vertex of degree 3, right? It never turns into a line. So that thing is not a curve, yeah? And so we have to formalize that a little bit in differential geometry, but it's actually not super hard to do. And I imagine most of you guys could probably do that. I had some fun with my drawing tool, tried to illustrate the definition of this neon-colored image here. So let's say that you give me the purple set, and I want to answer the question, is this set of purple dots really a line? Right? Well, the basic definition here is for any point P on the line, there exists some neighborhood around P. So that's like these parentheses here. I can cut out a little piece of that set so that there exists a function phi from the line into the curve. Does that make sense? So at every point, if I zoom in close enough, there exists a little function that parameterizes the curve. And this definition is going to be very important because this is essentially what we're going to extend to higher dimensional objects in future lectures. Notice this doesn't assert the existence of a function phi for all time. It just says like a little local neighborhood in time. Right? Specifically for curves, I think you can always extend that to all t by parameterizing by arc length. We'll go back to that in a moment. But in higher dimensions, that might not happen. You know? Now, specifically for curves, something that doesn't extend, but is kind of a useful notion, returns to the question that we just got a few minutes ago, which is what if I introduce t, like time, right? So in other words, I can define a second object called a parameterized curve, right? Or really, this is a function gamma of t, right? And in this case, sometimes it's useful for curves like the one I'm showing here, where it makes a loop-de-loop. So technically, if I view the curve as a set of points in the plane, this is not a curve, right? Because of that intersection point there. But sort of, there's an unambiguous way to kind of clarify that by giving a function gamma of t that gets rid of that overlap. Does that make sense? So typically, for the rest of today's lecture, we will assume that a curve is a function gamma of t, but we have to be careful what properties gamma of t has to make it really trace out a curve-like object and not just a point where it cuts. Yeah? That makes sense? Excellent. So a couple of vocabulary words here. If I have a function gamma of t and I'd like to refer to the geometric object, right, the set of points that gamma of t traces out, that is called the trace. I think that's reasonable here. And if I instead think of gamma of t as like 3 component functions x, y, and z of t, then they're called component functions. Sorry. Cool. All right. So our first sort of indicator that maybe something can go wrong with this particular representation of a curve is that it's very, very non-unique, right? I mean, if you go back to the example that I gave you, right, where you have the car driving along the curve and all of a sudden you jam on the accelerator and you double your speed, but it's the same object. Somehow, one way to view this is that it's a change of parameter, right? That essentially, if I have a function gamma of t, right, and now I warp time, like I have some other function which takes in a time and gives it another time, then that still traces out the same geometric object. Does that make sense? So if I have a function, in this case, g of t bar, so t bar is some other time, yeah? Then as long as it's increasing as a function of time, then I'm going to trace out the same piece of the curve. Cool? All right. So what I would argue, and indeed what I think the last 200 years of geometry professors have argued, is that any geometric conclusion that I draw about a curve traced out by function gamma of t should be independent to changes in parameter. In other words, if I stick some other, like I jam on the accelerator, and I say, okay, maybe curvature is the second derivative of gamma of t, right? Well, I would argue that that is not a geometric measurement, because if I change the speed at which I walk along this curve, then I get a different result, right? So someone doesn't have to do the geometry, it has to do the parameterization. Does that make sense? Excellent. So let's see here. So as an initial calculation for something that's going to be useful for us, the first question you might ask is the velocity of your curve dependent on the parameterization? The answer is obviously yes, right? If I move along the curve 2 times as fast, so the velocity gets 2 times as big. And so something that will work out really quickly is precisely what the dependence is. In fact, we'll also do it for acceleration. By the way, I got 6 emails after yesterday, the last lecture, that you couldn't beat the chalk. Please stop me. Don't be in here suffering, you know? There's an easy fix here. That said, I'm going to try and use this weird giant chalk. We'll see how it goes. Can I have a bigger one, please? Okay. All right. So my question. So first of all, what is the velocity of a curve? If I have gamma, gamma of t. That's not much better. Right? Yeah, this is going to be painful. This is the workout for the day. Then, what is the velocity? I know you guys know this. You've taken calculus class. Yeah, it's the first derivative, right? It's gamma prime of t, right? And we can say that that is equal to like the velocity of t. Cool? All right. So now let's say that I replace gamma of t with a new function gamma tilde, which is the composition of gamma and function phi. So phi goes from the real numbers to the real numbers. My question is, what happens to the velocity? Well, there's our favorite rule from calculus class. It's going to let us work out precisely that dependence, and that's called the chain rule. Right? So in particular, if we have d, oh man, gamma tilde, you're really going to make me do this. d, right? Well, we know when you have a composition of 2 functions, what happens is you kind of differentiate the outside thing and the inside thing. Right? In particular, we know that that's going to give you d gamma dt, and that's going to be evaluated at phi of s, right? Multiplied by what? Essentially phi prime, right? d phi ds, I guess in this case s. Does that make sense? You can all read this? Yes, Andy.
I was going to suggest if you turn on the front lights, maybe you don't have to write so hard.
Sure. Cool. All right. And because we'll find in a moment that that's a phi. We'll find in a moment that geometry is all about second derivatives. We're going to do that too. Yes.
Sorry, should that be d phi ds, not d phi dt?
This thing?
No, the one on the left.
This is a gamma for one thing. This is a problem with the giant
Sorry,
chalk.
yeah.
And no, it actually really should be. So the way to think about it is that remember this. You can think of phi as kind of like t, right? Phi is the input to gamma here. So you can think of the t's canceling, and you're getting the s here. So it really should be a t. Yeah, good question. Anything else? Excellent. And so let's take a look at the second derivative. We've done one caveat. I'm going to try the small chalk. If you can't see it, stop me. But the thing's giant. Okay. In particular, now let's look at the d squared. Actually, I think that's clearer. ds squared. Can we read that? We're good? Cool. Right, so what am I going to do? Well, I just have to differentiate this again, right? So this is the product of 2 terms. So I'll apply the product rule and then the chain rule. And what do I get at the end of the day? Well, I'll get, and this is d squared gamma d t squared. Right, I'm going to do the product rule just like before. And that's going to be evaluated at phi of s multiplied by d s squared. I'm going to write it down and then I'll tell you exactly what comes up. Plus d gamma dt composed with phi So do you guys see where this comes from? So remember the product rule, if I have the product of 2 things, I differentiate one times the other, plus the second one does it first. So the first one here, I differentiate this term here, right? So I get a second derivative in t, and then another one of these factors here because of the chain rule. And then the second term here, I differentiate just this guy. Okay. Cool. Yes.
Is that writing between the gamma and t and then?
Oh, the circle here?
Is that the component?
Yeah, that means composition. So this is like this function of that function. Great question. Yeah. Anything else?
The first time, there should be no square there, right? So when you derive the d gamma dt for second derivative, then the next one should be fixed. You don't derive that. Wait, how do you fix
Not
it?
quite, right? So I'm, here we're differentiating this term.
Yeah.
So when I differentiate this, I can say this is the derivative of this with respect to t times dt ds, right? So this is already differentiated with respect to t once, so I have to do it twice to get to this term.
No, I mean the second time.
The second. This time.
Yeah.
Yeah, so that's why you're going to square. You don't have a second derivative.
Oh, this square.
Yeah. Cool. Excellent. Good. All right. So so anyway, so the first thing we notice is that for one thing, when I went from gamma to gamma prime, even though I didn't change the geometric object, the velocity changed and the acceleration changed. Right. So we're confident that neither of those measurements is independent of perimeter. Right. But next we'll give you one that is, which is arc length, like the length of the curve. And what you remember from calculus class, so you can get the length of a curve from this formula. Can you guys all read the slide now the lights are on? Okay. And then there's like a YouTube troll that's like really annoyed that that stuff is blurry on the camera. I can't make you all happy. If you guys want higher cinematic quality, somebody in the back will have to deal with it. Right. And so I thought just as kind of a useful, very small scale differential geometry kind of calculation here, we can show that this thing is independent of the choice of parameter. Right? In particular, if I choose some function phi here, no matter what phi I put in there, I'm going to get the same value for this integral. Right? And that indicates to me that it's a geometric measurement rather than one involving the function. Does that high-level story make sense? Excellent. So, in particular, let's say that I did use gamma prime instead, and I want to know the length of that curve. Right? So then that would be the integral from a to b of, well, you can think of this like d gamma composed with phi. That makes sense. So now I'm integrating from 2 points along the curve, but I'm thinking of gamma tilde here, which is the composition of these 2 points. Right? Okay. So what are we going to do? Well, conveniently, I just worked out exactly what this derivative is upstairs. So I'm going to plug that in, and that's going to give me the integral from a to b of we have gamma prime of s times the norm of d gamma dt composed like that, ds. And hopefully you see that this is precisely what I've given you up here. Gamma prime is d phi ds. Cool? All right. So now, yes.
I'm confused with AB. Why are you still using AB the same one that you used for T? Wouldn't that change?
Oh, I'm sorry. I suppose all I did was really replace t and s.
Yes, I know, but I see.
So I haven't done any change of variables yet. Right. So yeah, so I was slightly sloppy. My notation on the screen is t. My notation here is s. You're absolutely right.
Oh, I see.
But now, in fact, to make you even more confused, I'm going to do the reverse change of notation and change variables to the parameterization for gamma of t. Have I totally lost you? You look very concerned.
So now you're using S as a parameterization. Just gamma
sorry.
is going from
Yeah, so
A
I'll
an
think of
interval
this
A0. So S is
the
defined on interval AB. Is that it?
Yeah, from s. That's what this number is.
Okay.
Okay. Cool. Good question. Yeah. Sorry, I'm sloppy with notation. Okay. So, right. So, what are we going to do for our change of variables? Well, it's pretty obvious, right? I'll take t is equal to phi of s, right? So, in other words, we can say dt is equal to, phi prime of s ds, yeah? Or equivalently, ds is equal to. This is where things get a little tricky because I'm going to swap s and t. But if you think about it, it's equal to phi prime composed with phi inverse of t inverse dt. Do you see what I just did here? So essentially all I did was divide by phi prime, and use the fact that I can get from S to T by applying a phi inverse. Cool? All right, so now if I use our favorite change of variables formula, I'm standing in front of the board, from calculus class here, right? So I want to take this as an integral over T, right? Then what do I get? Well, this is equal to the integral from trying so hard to write clearly. Phi of B, right? Of what exactly? Well, so now I have to put in T instead of this, right? So I get phi prime composed with phi inverse of T, right? Because this goes from T to S, and S is the input to phi. Yeah? Times, now we just have d dt, like we had before. Right? Now I get it's phi composed with phi inverse, so those cancel out. And then finally, I put in our formula here, right? dt divided by the norm of phi prime composed with phi inverse. Right? Look what just happened. I have this term cancels with this term in the denominator. Right? And what I'm left with is the integral from phi, I'll get out of the way in a second, I'm sorry, left-handed, to phi B of d, right? So do you guys see how I just proved independence of parameter? I said I can either measure the length of gamma tilde from A to B, or I can measure the length of gamma from 5A to 5B, and I get the same number, right? So in other words, this measurement of length doesn't depend on my choice of parameterization, because I can put in a new parameterization and get the same number. Whereas upstairs, right, when I put in a new parameterization, I compute velocity, I got something different. Cool? So if you take a differential geometry class as an undergrad one, you will spend your entire life doing like this check for like every single geometric object you define. Like it's like, oh, like I really like this thing, you know, I want this thing to have some formula involving the second derivative. And then the first thing that will come out of your professor's mouth is like, is it independent of the parameterization? And then you have to go through some irritating change of variables calculation to make it work out. For the most part, we will skip that in this class because we have the pleasure of teaching you differential geometry and computational stuff all at the same time. But this is an example of the kind of calculation you do. Right? You define some object which might have to do with the parameterization. Right? Like here, this definition of arc length depends on that function gamma of t. And then your homework is to show that if I reparameterize, I get the same thing. Yes?
I have a question that might sound a little bit philosophical, but I'm wondering if there is some fundamental reason why some of these geometric quantities don't depend on parameterization.
Absolutely. Yeah, so for instance, you could take this length and you could define it a very different way, where I take this line and I cover it with little line segments and I sum up the lengths of all the line segments, right? And then you can show that if you take the soup over all the possible sums of line segments that sit on top of the line, you get the arc length. Right? And you remember the definition of the Riemann integral? Right? The integral of a function is like kind of like you take little rectangles and you add them up. That's precisely that definition. Right? So that's how you can in fact derive this definition of arc length. Right? So typically, as you say, the kind of philosophical aspect here is maybe you start with some geometric measurement that's purely geometric, has to do with distances. You realize like without calculus, it's a huge pain in the tuchus to actually do anything concrete. So you write down some formula like this, but then you have to do your homework and check that you haven't broken geometry. Cool. Any other questions? All right. Great. Then we'll go back to pictures here. So I might try and turn off this light for now, just because I think it's easier to see. Right. So one. You know what? It's fine. Okay. So one question you might ask is there like a canonical choice of that function phi? Right? And the answer is actually yes. This is called parameterization by arc length. If you're a differential geometer, you say that phrase 3 times every time, you know, while you're brushing your teeth and go to sleep. And essentially, parameterization by arc length says, I'm going to, instead of having some arbitrary time that's, you know, determining where I am, as you know, for every time I have a position on the curve, well, there's only kind of one, if you think about it, you know, up to constant shift, only one reasonable way to do that in a canonical way, which is to say I drive along the curve with constant speed. Right? In other words, I don't hit the accelerator, I just go at unit speed for the entire time. And that's called parameterization by arc length. So eventually that function phi is going to be nothing more than arc length. So it says, like, effectively what it's saying is move 3 feet along this curve, right? So that number s would be the 3 feet, and then it's going to be the point 3 feet away by arc length. Does that make sense? Parameterization by arc length is actually quite important for even practical purposes. So here, this is an image of a spline where somebody's taken some text and warped it along the spline, and then kind of spaced the letters based on T as opposed to S, which is arc length. And as you can see, the letters end up all the same size if I space them out evenly by arc length. If I space them out evenly by parameter, whatever this parameter is, I think it's some spline thing, you get squashing and stretching depending where you are, because the car, again, is speeding up and slowing down as you drive along the curve, which is noted. Okay. Right, so obviously the length of a curve is not enough to describe all of its geometry, right? If I take this string, I can put all kinds of different conformations and still has the same length, right? So we need something else to give a complete geometric story. And that additional object is something called curvature. Right, so one thing that's very easy to check is if you parameterize by arc length, you put in that arc length function as phi of t, as like what we've done on the left here. Wow, my eyes feel weird. Then you can check that the first derivative has unit acceleration, or velocity rather. This makes sense because essentially I'm moving at 1 unit per unit. Like when I move 1 foot, I move 1 foot along the curve. And then the question might be, what is the second derivative of the curve, for one thing, and how can I express that? Now, there's something else a little fishy about the geometry story from a philosophical standpoint. Because if I take a curve and I just kind of rigidly move it around in the plane or like rotate it, but I don't stretch it out or squash it, somehow I haven't really changed its geometry, right? But my function gamma of t is going to change drastically, right? I'm going to rotate, add, whatever. And so one question that comes up in the theory of curves quite a bit is what is the natural frame to express a curve? In other words, the x and y axes were kind of just made up by me to stick the curve in 3D space. But if all I really care about is the geometry of the curve itself, then x and y are totally arbitrary choices. So people in differential geometry had a really clever trick for describing the geometry of a curve, which is to say, the only object I have in front of me is the curve itself. So any frame that I have to choose has to come from the curve. Right? So in particular, if I want to understand the geometry of my curve around this point down here, well, there's only one frame, which is, maybe I take the unit tangent as like the x-axis. And well, now we're in the plane, so there's only one y-axis I can choose which up. So it's like rotated by 90 degrees. Right? And this is what we might call the intrinsic or moving frame of my curve. I say it's moving because as I move along the curve, obviously the tangent's changing, so this t and n frame change, n sensitive. Does trick make sense? Now, essentially, it's this kind of philosophical point here that differential geometry should be coordinate independent, but there are a lot of calculations that we do that need coordinates. So the only ones that we can choose are built from the curve itself, because anything else we do is some choice that I made as an engineer and not as a mathematician. Right? So in other words, referring to x and y explicitly is sometimes a hack, although it's also quite convenient. And in fact, I would argue, typically when you see really messy calculations in differential geometry, which happens a lot, like if you open Wikipedia and you look up like curvature tensor or whatever, you're like, it's a nightmare, I can't read this stuff. A reason for that is that people really, really like coordinates, and geometry doesn't like coordinates, and so somehow the end result is that your formulas are just really messy. Right? So actually it's kind of a cool high-level thing that when you do it right, all of a sudden everything comes out quite nicely. And there are a few textbooks that really go to that extra effort, although then they end up on the opposite side, which is like developing a giant algebra and then chaining them all together and you kind of forget what you were doing. So anyway, no matter what, you're kind of hosed to it, but if you don't like symbols, there's a way out. So really the question that comes up when we talk about the geometry of a curve is how do you understand a shape if you don't have a system of coordinates, if you don't have x and y? Right? We've already kind of answered that, which is by describing things inside of the frame of the curve itself. Now, really quickly, we'll prove my very favorite lemma from all of calculus, which is, let's say that I have a function that goes from times t, and it maps to vectors v of t, and I have an additional property here, which is that the norm of v of t equals 1. Right? This is exactly what we have, like the unit tangent is an example of such a function. Right? Then, my question is, what does the derivative of v, that's a t, look like as a function of t? And there's a really nice trick for this. So I'm sure a lot of you guys have already seen this. So if you haven't, you should. So I'm going to expose you now. So first of all, what is the dot product v of t dot v of t? 1. Thank you. Right? That's the norm of v squared. Yeah. Let's differentiate both sides of this. Right? So on the right-hand side, I get 0, right? The derivative of 1 with respect to time is 0. Left-hand side, I use the product rule. I have the same thing twice, right? So what do I end up with? I end up with 2 times v of t dot product of v prime of t. World's easiest little lemma to prove. But it's actually geometrically really cute what just happened here, right? Which is, if I have a curve that is essentially sitting on the unit circle or the unit sphere, and I look at its velocity, then I always have the property that v of t, the dot product of v of t and v prime is 0. In other words, they're perpendicular, right? So if I look at the derivative of the unit tangent of my curve along the curve, I am guaranteed that at every single point along the curve, this picture is right, that it's parallel to this direction n. It's 90 degrees rotated. Now its length doesn't have to equal 1, right? The acceleration could be non-trivial, but it has a kind of a direction that's easy to predict, at least for planar curves. That makes sense? So essentially, the way that I would describe the curvature of a curve is I'd say, okay, well, let's take a look at the unit tangent to my curve. Right? So for one thing, if I'm traveling along a straight line, and I look at the derivative of the unit tangent with respect to time, what is it? It's 0, right? Because the unit tangent is just pointing right in front of me and I keep walking. Right? So essentially, when my curve has curvature, and it's like an interesting loop-de-loop kind of thing, that corresponds to my moving the steering wheel, or in other words, changing the unit tangent as a function of time. That makes sense? So when you talk about the curvature of a plane curve, the definition of curvature is nothing more than how much I push the steering wheel. And another way of putting that is I look at the derivative of the unit tangent, which we know is 0 if I'm moving along a straight line, and I just look at its length, right? And that thing is called the curvature of my plane curve, right? So in other words, I can use very slick notation to write what I have on the screen here. I don't think this is something that's out to drive on the board, but if you look at dt dx, well, we know what I just showed you here is that it has no component in the t direction. It has to be orthogonal to t. So in fact, it's some function of s times the normal, and I'm going to define that function of s to be k of s, and that's the curvature, right? And similarly, so the normal is a unit length vector, so when I differentiate with respect to time, right, what do I get? Well, I get something orthogonal to the normal, yeah? And well, there's only one direction orthogonal to the normal, which again is the tangent, so that explains sort of the zeros in this matrix here. Yeah? And it's pretty easy to see the derivative of the unit normal has to also be some multiple of curvature. Why is that? Well, look at the way that I define the unit normal. It's just the tangent rotated, right? So if I take the derivative of the tangent and get k, if I take the derivative of the normal, I'll get k rotated. Yeah? Cool. And it turns out that this is what really tells you the interesting information about a shape, this function k of s. And there's so many different ways to understand it. We'll explore a few of them in lecture today, or next time, depending on timing. One thing to note is if you take 1 over k, this is an object called the radius of curvature. This is kind of the picture you should have in mind. It's like the radius of the circle that just barely touches or osculates the curve. Right? Fun fact, in what I think Latin, osculate means kissing. It's relative. And in fact, the really fundamental theorem here is that if I know the function k of s, if I know the rate at which I'm pushing my steering wheel, I have determined my curve and the plane up to range of motion. In other words, k is all I need. Right? And the nice thing about this function k is that I did not need coordinates to compute it. Right? That was the whole point of how we did it. This is kind of slick. Right? I have this measure of curvature that can tell me everything I need to know about the curve as like a nice numerical measure. And it's independent of sort of embedding is the fancy way of putting it, or how I stuck it in the plane. Did I see a question? Was that just a...
No, I have a question.
Yeah.
This might be an edge case. Would you have a curve that like touches itself at a place where the curve like it doesn't look like an intersection? If you zoom in, they're like parallel to each other.
I mean, that's perfectly fine as long as you have this function s, right?
There's two curvatures that
Yeah, right. And what I would say is that it is not a curve. It is a parameterized curve, but it's not a curve. Right? So if you have like a letter x and it goes like that, that is not a curve.
Well, yeah, then they connect to each other down there.
They can't connect. I mean, that's just not a curve is a locally one-dimensional object. If there's a point of intersection, it's not a curve. So if you have a function of
not
t,
like
that
an
is a
algebra
bigger
x, where like you've got like it's two friends. Here.
yeah, they're still touching, right?
Yeah, they're touching, but
At the point that they touch, it's not a curve.
they're not crossing. Like they have.
Doesn't matter. They might agree in curvature. In fact, the way I define it for you, they know that the curvature would be different at the sign, but depending on how you orient those two pieces. But it's not a curve. Yes?
Quick question or slash comment. It feels as though there's like already a notion of handiness that comes into play.
Absolutely. The one thing that is true is if I turn my car around, I make 5, there are 2 parameterizations by arc length. One where I move plus arc length, the other where I move minus, and then the curvature changes sign. Yeah, that's good. Excellent observation. And that's going to matter when we talk about surfaces like what is this thing called? You twist and you glue. Mobius strip, right? Where there is no orientation. Then you're only going to be able to define curvature of the sign. Lucky for us, the plane, when I say rigid motion, I don't include reflection in it, so somehow that's unambiguous. Yeah. Any other questions? Cool. Fun thing about this theorem is that actually the statement of the theorem is shorter than the name. Yeah, I have a differential geometry textbook I was looking at. Okay, so there are many different ways to prove this theorem. The nice thing about the 2-dimensional planar version is that it's very easy. It's like a calculus exercise. One way to go about this is to say, well, if I have the unit tangent and I'm in the plane, then there really exists some function theta of s, right, which is just the angle of the unit tangent, say with the x-axis, right? So in other words, I can think of t of s like, this function that I'm showing you up here. Does that make sense? So if I do that, then what am I going to do? Well, I differentiate t of s, right? What do I get? Well, by the chain rule, once again, I get theta prime of s times, minus sine s, and then cosine, right? And it's very easy to see from here that this thing is a unit vector, right? So in other words, this object here is exactly the curvature. Incidentally, this gives yet another interpretation for curvature, right? It's the kind of the angle, the rate of change of the angle of the unit tangent as you move along the curve, right? And essentially, proving this theorem is simply going in the reverse direction, right? Integrating from here to the curve itself. Cool. So that basically closes the entire 2-dimensional picture, right? A single function, kappa of t, is enough to tell me the entire geometry of the curve, right? Which is pretty neat. And of course, the next question you should ask is, what is the 3D version of this story? It becomes a little more complicated than that. We get an object called the Frenet frame, right? Or the moving frame along the curve. And the idea here is, if I have a curve in 3D, it still has an unambiguous tangent vector, right? So then what do? I take that tangent vector, I differentiate it once, and I say I define that new direction to be the normal, right? Because there are now 2 directions I could have chosen from, effectively, right? But I define that thing to be n, right? So now I have a notion of curvature, because curvature is the thing I get when I differentiate t, and somehow that's nice because it agrees to the planar case. You know? But now I have 3 directions, so when I differentiate the normal again, well, we know the derivative of the normal can have no component in the normal direction, right? But it can have a component in 2 other directions, right? The tangent direction and some third thing. So, since we're all grown-ups here, what do? We give that third thing a name, and we call it the binormal, which is essentially the stepchild of the normal and the tangent, right? I have 3 axes, I get 2 of them naturally, so I take the third one to be whatever's left. Yeah? So this set of relationships here is actually quite natural, right? What it says is, I define curvature to be the length of the derivative of the tangent, right? So that's why there are 2 zeros in the first row, because this is by definition. Then what do? I differentiate the normal, and I say, well, I don't actually know what the derivative of the normal is. All I know is that it can't have a direction parallel to the normal. So there are 2 other things. The first one I can check agrees with the first guy. The second one I just call something else. I give it a new name. That's a function called torsion, right? And then you do the derivative the third time, you get this as the third row. It's called the moving frame of a curve, and if we're really lucky, so give it a little animation here. Right, so you can see how it kind of works. The normal is kind of pointing inward at the curve, and the binormal is this thing that points up. Right? And so roughly the intuition here is that the tangent is tangent. The normal or this curvature function kappa is measuring in plane motion, and the torsion is sort of how much you're leaving the plane. Right? So if torsion is 0, end up in the plane. And just like we have the fundamental theorem of the local theory of plane curves, we also have the fundamental theorem of the local theory of space curves, which is a slightly bigger headache to prove, not much bigger. which says that if I have these two functions, kappa and tau, those things completely determine the curve. That sort of makes sense, right? Because kappa is saying all the in-plane motion, and now tau is just telling me how much I leave the plane. So I put them together, I get something 3D. It's a very high-level argument. We don't have time to prove this stuff carefully. Now, one question that I always get in lectures like this at about this time, I wish you guys hadn't, but since I have, but since you haven't, I'm going to ask it for myself, is what happens in more than 3 dimensions, right? Like, can I take this theory and somehow extend it? And the answer, actually, typically you don't learn in geometry class, but the answer is yes. And so the trick here, this is a generalized Frenet frame, and I've given you the original reference that dates all the way back to the 1800s. And essentially, you do kind of the stupidest possible thing where you just keep taking a bunch of derivatives of your curve. So you're in n dimensions, so you need n derivatives, right? Same where you had 3 derivatives for the 3D curve. And then what do? I just kind of orthogonalize them, right? Like I just take these different derivatives, like the velocity, the acceleration, the jerk, I guess. And if I just orthogonalize them, like I just get rid of components that are parallel as I move along, then I get a moving frame just by definition, right? Essentially, all I'm doing is taking the matrix whose columns are, all the different derivatives of my curves, and then doing like QR factorization of it or something. And what I get is the Frenet frame. And this is some nice generalization to higher dimensions. If you don't have a great intuition for this, neither do I. Every time I see this, my suspicion is that somehow it's useful for time series and machine learning, but I've never quite been able to write it down. So if one of you guys does that for your project, that'd be cool. Okay. So essentially, that's the theory for curves. It's quite simple. If I have a curve embedded in n dimensions, then I need n-1 functions to define the geometry. Right? So for a plane curve, I have curvature. For a 3D curve, I have curvature and torsion. Now, these things are essentially derived by taking the unit tangent and then differentiating it more and more times with respect to arc length. Cool. So I should pause here. Any questions before we move on to the computational stuff? Yes.
Is this notion only valid if the embedding space is Euclidean?
Great question. So we're going to move on to, yes, roughly, but you have to be careful how to construct this stuff because, yeah. I mean, the smart answer is yes, because you can always embed stuff in Euclidean space, right?
Okay.
Yeah.
Fair enough.
Okay. Right. So anyway, the question which I've left myself not nearly enough time for is how do we do these types of calculations in software? How do we write code that approximates things like curvature? So we'll start with this today, and I guess finish it on Tuesday. So you have enough for most of your homework. Now the kind of old school approach, like we took 6, 8 through 7, would be to define all this stuff in terms of like a spline curve. So I have some quadratic thing with control points, and I try and compute the curvature using one of these formulas that I've given you here. And this is nice because these are nice smooth curves. I can differentiate them, from here until Sunday, right? But the question I would ask you, like get out a scrap piece of paper and just play with it if you're bored, is what is, if I give you a cubic Bezier curve, like I give you a function that's like a cubic function of t, and I try and compute this integral for arc length. I dare you. And what you'll find is that it's not a pretty function. and in fact, sort of taking these nice ideas from differential geometry and making them work on things like splines that we like in computer graphics is really, really hard to do. And this is in large part why some of this area of computer-aided geometric design really struggles to deal with things like, I have 2 curves and I want them to join with the same curvature. Okay, so I kind of splice together 2 splines and I want them to have a nice intersection. It's really, really hard to do that because that curvature function is so complicated. Right? And in fact, the reason I challenge you to do this is because I happen to know the arc length of a cubic Bezier curve. We don't even know it in close form. There's no formula. Right, so the sad fact here is that really there are very few closed form expressions for nice smooth curves to compute things like arc length. Curvature you can always do, right? That's just the differentiation, but it's probably not very nice. Right? And so when you do have these formulas, they're very messy. Right? And so, and really, to make matters even worse, things like Bezier curves and all these things from old school, computer graphics, are not the whole set of curves anyway. There's some approximation, right? I can't like draw an arbitrary curve in the plane and call it a cubic curve, right? So what the philosophy has been more recently is go in the opposite direction and say, okay, well this doesn't cover the set of curves anyway, so if all we're doing is approximating, let's take the stupidest possible approximation. Namely, let's take a curve and just code it with a bunch of line segments. Right? Because calculations of line segments are easy, right? And sort of, it's easy to think about these objects. And so the fancy phrase here is that I will have a piecewise linear approximation of a curve. Right? So in other words, instead of having a smooth object, I approximate with a bunch of lines. Cool? Okay, but like I mentioned a couple lectures ago, there's a big problem here, which is that like if I want to take all the formulas I gave you from before and apply it in this case, I'll get something super boring, which is like curvature is 0 on straight lines, and then infinity every time they meet. Right? So like the question is, what is kind of the right way to understand these theories in the discrete case? And just like we talked about before, there are really two different approaches here. Either I could take kind of a calculus thing, idea here and say, maybe I approximate derivatives with finite differences, right? Like, you know, this is the derivative f prime of x is the limit as h goes to 0 of this thing I've given you here. Maybe instead I just choose a positive h that kind of aligns where I have those dots and approximate all these derivatives that we use to compute curvature. And then the types of theorems that you prove are sort of, as I make my sampling of my curve smaller and smaller and smaller, my approximation converges to curvature. Or we can kind of have a reality check here, which is on a computer, h is always going to be bigger than 0. We can't take that limit, right? And so for nice properties of curvature, the most we would hope for in that kind of regime would be approximately nice properties for discrete curves. And so an interesting question is that really there are two different sort of key considerations when we discretize these others. One is, I mean, you really do want to replicate the continuous theory, and it's important to understand convergence. But the second one, I would argue, is almost equally as important, which is what is the behavior in the discrete regime? That is, if I choose h greater than 0, like, am I going to have a ridiculously small h before I get something that looks like curvature? Or do even very coarse approximations of my curve give me some nice notion of bending, for example? Okay. And so we'll kind of examine some discrete curvature theories as one way, an alternative way of understanding these things beyond just divided differences. Right? To acknowledge that there's more interesting stuff to be done. Okay, notice this is theories. There's not one single theory of curvature in the discrete case. And just like we talked about the Laplacians from a very high level 2 lectures ago, different curvature theories give you different conserved quantities and different properties. And one of the really irritating properties here is that you have no free lunch. No single theory of discrete curvature will give everything you want. So, to start out with, how am I doing on time? Okay. We're going to define an object called the Gauss map, which we already kind of defined, but I didn't give it a name. Which is going to be for planar curves. Right? And this function for a planar curve, like what I showed you up here, is the map from the curve to S1. How many of us seen this notation S1 before? It's just a fancy word for the unit circle. So it's going to take every point on the curve to the unit circle and give you the normals of the curve. Right? So that's what this picture is giving. Right? So this function n of t is exactly, that we already defined a couple slides ago, is exactly what is the Gauss map. Cool. So just like I told you before, right, we can define curvature using this nice formulation here. That is the derivative of theta. And essentially the way you can see that is that, if I take t prime, then I get theta prime over here times this unit vector. Okay. So from this perspective, so k of s, let's say I have a closed curve, right? There it is. And I have a function k of s, and he's equal to theta prime, right? And now, I'm going to parameterize this curve by arc length, and I'm going to return to the same point eventually because it's closed. Right? So in other words, there are 2 times t0 and t1 that hit the same point. Right? Then what happens if I integrate from t0 to t1 of k? Well, remember k is theta prime, and of course the integral derivative is nothing more than theta again. Right? So in other words, this is like theta of t1 minus theta, oops, that's a theta, of t0. Yeah? You guys see that? Okay. Here's the thing. I ended up at the same point. Right? So if I'm looking at, and it has the same unit normal. Right? So n is the same at these 2 points in time. So what is this difference in thetas? 2 pi. Yeah, because I went around the circle and the normal traced out like that, right? So theta continues to increase, and eventually it makes it all the way around, but it makes a closed loop. And as we all know, the sum of angles around the circle is 2 pi. Now similarly, if I had a curve that went and looped over itself twice, like that, now it goes twice, and it would be 4 pi. No? This is something called a topological invariant of my curve, or the winding number, which is the number of times that the normal vector turns around itself. right? And I can get it by integrating theta all the way along the curve until it meets up at the same point. Does that definition make sense? This is called the turning number or winding number. And I'll give you some examples here. Returning to this question about orientability, you can notice if I go to the curve on the left here, I get a different winding number from going to the right. And that's because I have some notion of what's clockwise versus counterclockwise. Even if I didn't have that, by the way, there's ways to get the sort of unsigned version of this, but that's a little more complicated. Okay. So now, what are, and again, if we want to get theta, the difference of theta, what I do, I just integrate curvature, and that's pretty clear from this relationship here. And the turning number theorem, which essentially I just proved for you by accident, is that the integral of the curvature of a closed curve is always equal to a multiple of 2 pi, and that multiple is called the turning number of your curve. Cool? You didn't know that? Now you do. Kind of a fun fact. So now the question is, let's say that I define a discrete curve, right? It's just a big pile of line segments. And I approximate curvature with divided differences, and I sum up all of those curvatures. Chances are I won't get a multiple of 2 pi. I'll get like 2 pi plus or minus 0.001, some approximation. Which is, can I define a curvature so that I preserve this winding number theorem exactly? Right? And the answer, obviously, because I keep talking, is yes. So one way to view this is that there's some kind of discrete Gauss map going on, where essentially every line segment has an unambiguous normal direction, right, just the direction perpendicular to the line segment. And then every time there's a juncture, the normal direction just kind of rotates into the next guy. So in other words, it's not just that I have 0, infinity, 0, infinity. It's more like a 0, and then like a nice happy turn, and then 0, and then a nice happy turn, and 0. Right? And I would like somehow, so the way to understand this again is that edges become points in the Gauss map. Cool? Because they have a constant normal. And vertices become arcs, right? Those are the transition from one normal to another. Okay. So now I'm going to recall a theorem that you might not remember from 9th grade, which is something about the exterior angles of a polygon. Okay? If you don't remember this one, you should go back to your 9th grade geometry textbook. I promise you it's there. Which is, if I have a polygon, like this green shape that I've drawn you here, and I look at the exterior angle, so I take every edge and I extend it a little bit, and I look at the turning angle from that to the next segment, I have a closed polygon, then the number that I get is 2 pi. Or more generally, I'll let you kind of convince yourself at home, if this polygon wraps around itself, I get a multiple of 2 pi. That sound familiar? Cool. So what did we do? Well, we just found a property of discrete curves that looks an awful lot like the property that we kind of want for a definition of curvature. Yeah? And in fact, to make matters even better, I mean, somehow, this even kind of looks like the same definition that we have for T prime, right? We're kind of measuring the change in steering wheel as I go from one segment to the next. Yeah? So there are a lot of different ways to explain this. One way to view it is that sort of you can look at this piece of your curve from the midpoint of one segment to the midpoint of the next, and that this one turning angle theta is sort of describing the total curvature along the union of 2 line segments. Does that make sense? Cool. So another way of viewing that is that this turning angle theta is kind of like the integral of curvature along this little piece. Right? Because if you took that theta and just distributed it along the 2 adjacent guys, that's what you get. This is an engineering approximation. I'm like defining stuff here. Right? This is not, I mean, this thing's flat. Yeah? I hope we all agree. Yeah. Okay. So, well, if I wanted to approximate curvature, how could I do it? Well, given, if I think of this theta as sort of the total curvature in this little segment, well, remember that curvature is the root of theta, so maybe I divide by the length of the segment, and I have an approximation of curvature. And in fact, one thing you can check is that this approximation is convergent to the actual curvature of the curve. I sample it more densely. Yeah? Now, there are a couple weird properties. So sometimes we mistakenly think of this angle theta as a curvature of the curve rather than theta divided by this sum. And that's actually incorrect. One way to see that is, let's say that I take this right angle, and I have this angle theta, but I sample it more densely and I still have the same right angle. Somehow, that more dense sampling indicates to me that there's a very sharp turn at the corner here, whereas on the left-hand side, it could be there's actually quite a smooth turn here. Right? But the angle theta remains the same. What changes is that the length of stuff that I'm dividing adjacent to theta got smaller. Okay, so curvature increases. That make sense? Cool. Yeah. So we've got the same integrated curvature, but not the same, kind of imagined curve sitting in these pieces. Okay. So another way of viewing this, which is going to be very important when we talk about discrete exterior calculus in a few weeks, is that somehow we have the same integral of curvature in these two cases, but we don't have the same actual curvature. And then often what's going to be more useful for us is keeping track of integrated quantities than the quantity itself. So in this case, you can think of curvature as integrated over what we call a dual cell, like kind of the piece of the curve that's closest to this vertex, and not something. This is going to be a theme that comes up when we talk about triangle meshes. It's going to be way more complicated, and I'm going to screw it up in class really bad, so get excited. Okay, all right, so one thing you might ask then is, can we prove the turning angle theorem? And now the answer is really clearly yes, right? So here, what do we have to do? We have to first kind of make a definition, which is, what does it mean to integrate curvature over this entire discrete curve? Well, I think we can all agree that it's the sum of integrating curvature along each of these dual cells, right? The integrals break up like that. Well, I just defined for you the integral of curvature along the dual cell to be the turning angle. So now I have the sum of all the turning angles, and like we know from geometry class, that's nothing more than, 2 pi k, or k is y nu. So what did we just do? Because I haven't been excited enough, this is super cool. We defined a discrete notion of curvature. It's like convergent, it's a nice approximation, but it also exactly preserves this topological theorem, right? I can get a global statement about the geometry of this curve by making little local measurements. And that's what's really neat, that if you design these geometric measurements in just the right way, I can derive this stuff without making any approximation. Yes?
So is there like a corresponding shape to this where it's like arcs of a circle with that like are stitched together?
That's a weird noise. The short answer is kind of sorta. Like yes, I could give you circles with radius 1 over kappa, and then you have a corresponding shape. Making them actually meet up at the edges of the dual cells is quite challenging. Yeah, so there might be, but I don't know of one. Yes?
So I was thinking the notion where you actually divide by the length of the segment,
Yeah.
and then you showed those two identical curves but with different segments, that notion is not geometrical.
Yeah, that was an approximation, right?
Okay, so but that notion of literature doesn't preserve the fact that your notion of curvature has to be only dependent on the set of points, as you said. So if you have
Not quite. So it depends on the geometry is okay, right? I mean, the length of a line segment is certainly a geometric measurement.
No, what I'm saying is that if you have those two curves and you pretend you didn't discretize them, they look exactly the same independently of where you put your points. So geometrically they're the same object.
Oh, it's true. If you sample the same smooth curve 2 different ways, we'll get to do 2 different curvatures. Absolutely.
Okay.
I mean, there's yes.
So
Right? I mean, in a sense, like another way of viewing that is like these points could explain a lot of different curves, right?
Yes.
So what we're after is not necessarily like the curvature of the smooth guy, because it's not really possible to sense that from a discrete sampling. But we're after a notion of curvature that makes sense. And so this actually relates to the previous question, which is, does there exist a curve that somehow agrees with this curvature measurement? Right? And things with constant curvature are called circles. So it's difficult to assemble a curve out of circles, but you could approximate pretty nicely. I know this is kind of a half answer. This is an approximation of curvature from that perspective, for sure. Yes?
It seems like it makes sense to use the midpoints of the lines, but it also seems arbitrary to use other points along the line.
Absolutely, yeah. And this is, again, kind of an engineering decision, right? So for curves, I would argue it's kind of, there's really no other choice to make here. Maybe, I don't know, prove me wrong. But there are other theories where that's certainly not the case. For example, in a triangle mesh, when I take an integral over a triangle mesh, I have one number per vertex, right? I need to kind of give a dual cell, which is like the area around that vertex, and I'm going to multiply it by. And what we'll see in this class is that there's at least 3 different formulations of that I can think of that different people use. And as long as they all go to 0, as the length is small, there can be some consistent theory, but there's no single choice. Good question. Anything else? Okay, so remember I told you there's no free lunch here. One definition that you're going to work out on your homework, if you haven't already, is that you can prove that if I take a smooth curve and I look at the arc length, and I ask for the vector field along the smooth curve that decreases arc length the fastest. That makes sense? So I want to take this curve and kind of straighten it out. Right? It turns out that that vector field, as you'll show in your homework, is equal to minus the curvature times the normal. Which kind of makes sense, right? If the curve's kind of bumpy, it wants to push in the bumpy stuff toward the center, and the more kinky the curve is, the more it wants to push toward something flat. You know? That's roughly what this is saying. Well, so this is a property of smooth curves, and I might ask, can I get a theory of curvature that agrees with this property of smooth curves? That if I take the gradient of arc length, I get curvature times the normal. And it turns out, if you check, the theory of curvature that I just laid out for you from turning angles does not give me this property. In fact, what you'll show on your homework is that if I take the gradient of arc length of a discrete curve, like unambiguously, should be the sum of the lengths of the segments. If you do anything else, you're really going to have to convince me that that's the right thing to do. So if I take the gradient of that function as a function of the positions of those vertices, and then take the norm of that, then I won't get the turning angle theta, but instead I'll get sine of theta. And I get some other thing. That's really disappointing, right? I have two different properties of smooth curvature that I'd like to both be true at the same time, but they're just not. I can't get the turning number theorem, and that if I take the gradient of arc length, I get curvature, both for the same definition of curvature. See this example of this no free lunch property. But anyway, you'll work this out in detail in your homework. One thing to notice, just as a sanity check, of course, is that if the angle theta is very small, sine of theta looks a lot like theta, right? Which is essentially saying that as I take my curve and I refine the approximation, I add more and more samples, these two approximations of curvature will agree. So it's not like they're like drastically different, but they're different in the regime where I sample coarsely rather than very densely. Does that make sense? Cool. Right, so of course the remaining question we really should answer, but it's a little bit outside of the scope of the calculations we know how to do in this class, is does this discrete curvature conversion the limit? One thing that is pretty obviously true is if my first curvature converges, then this one does too, because two are sort of the same. And in fact, you'll have to trust me on this one, they both really do converge to the actual honest to goodness curvature of the two-dimensional plane curve. Cool? So there are all kinds of different questions, of course, from the kind of numerical analysis world, right? Like how fast does it converge? How many samples do I need? If I'm like really evil about placing my samples, like I put 1 million over here and like 3 over there, is my curvature approximation very good? No, probably not. So all of these things are very important and really are better covered in a numerical analysis class, but stuff you really should think about, if nothing else empirically, like just invent a curve whose curvature you know at home and try these different approximations out, right? So that's certainly not hard to do. Cool. So the area of discrete differential geometry is really fun, right? I mean, essentially we have two different notions of curvature that have different discrete behavior, right? Theta and sine of theta are two different numbers. But in the limit, they both converge to the same object. And that's sort of this weird contradiction that we end up with a lot in this world, is that there are lots of measurements that we'll make in the smooth theory of differential geometry that are completely unambiguous. But then in the discrete theory of differential geometry, there's like engineering decisions you have to make, and it's not clear which one is right because they all have different trade-offs. Right? There's no single best answer here. Yeah? So I'm kind of giving you a waffly answer, and the reason is because that's all mathematically, for whatever reason, that's just what we got. Yeah? Right. So the next question, of course, everything that we've done so far is for 2D curves, and for 3D curves, we might ask the question of whether there's a corresponding notion of Frenet frame. And of course, the answer is yes. I mean, people worry about all this kind of stuff. So I think, so again, remember our goal here is to derive now these 3 vectors t, n, and b associated with the 3-dimensional curve, which is basically a big class line segments. Cool? All right, so this problem actually shows up in all kinds of different literature. The 2D curve stuff, not quite as much because it's still a little bit of a toy problem. But the 3D one, for example, actually I think some of the earliest references that I could track down were in kind of the computational biology protein folding world, where you can think of a lot of these biological kind of macromolecules as lots of little line segments, right? Lots of little connected together atoms. And so some folks are even, kind of applying Frenet frames to understanding how, proteins and so on fold and how that folding changes and what preferences for different folds these objects have and so on. Kind of cool to see. And so, unfortunately, the discrete differential geometry perspective on the Frenet frame is a little bit, I couldn't find much. And there's actually a couple of reasons for that I'll sketch out in a moment. There's one that comes from this this paper from 1932, actually, and it gets picked up occasionally in the kind of macromolecule world, where they say, okay, the tangent in the Frenet frame is pretty unambiguous, right? I mean, we're pretty sure that should be the individual line segments along the discrete curve. So we're only really missing n and b. And in fact, one way to think about this, remember that, again, the binormal is kind of like measuring the out-of-plane motion of your curve, and the normal is kind of like the in-plane motion of the curve. So if I take 2 adjacent line segments along a 3-dimensional curve, those actually sit in a plane, right? So I can kind of think of the normal of the curve as sitting in that plane, right? So what do these people do? They say, okay, well if the normal sits in that plane, then the binormal, since it's again like the little sad stepchild of the other two, has to sit out of the plane because there's just nowhere else for it to be. Right? So we say, okay, we're going to define the discrete tangent to be this first guy because like kind of what else would it be? Right? Our next job will be to define not the discrete normal, but the discrete binormal as the cross product of two adjacent tangents, because it's going to be perpendicular to the plane that those two adjacent tangents sit in. And then we say, okay, well, the tangent direction, or rather the normal direction, is whatever's left, right? The third normal direction. This is kind of the usual theme in differential geometry. You compute two things, the third one is three, right? Yes?
So this kind of changes in the middle of each segment?
Yeah, excellent question. This is precisely the thing I was going to point out, is that here, the tangent and then the normal and the binormal live in different places. And there's actually, the question about like what is the dual cell and like why do we define it this way really comes into play, even just in this case of 3D curvature of a curve. Right? The tangent sort of unambiguously really should be the line segments. If it's not the line segments, you're going to have to engineer what it means to be tangent at a vertex where two line segments meet. But then for these guys, what they notice is that it's actually more convenient to approximate the tangent along line segments and the normal and the binormal at the vertices. Right? And in a sense, that's perfectly fine. I mean, who says they all have to live in the same place? But it does make, for example, talking about the Frenet frame at a single point on a discrete curve a very difficult thing to do. Right, and so, in fact, what's relevant to their application is what they call bond and torsion angles. These roughly look like curvature and torsion, and again, they measure sort of the change in normal and binormal, which is some measure of the curve. Yes?
How to define the binormal plane if two adjacent tangents are collinear?
I'm sorry, could you repeat that?
If two adjacent tangents are collinear, how to define the plane then?
Ah, what an excellent issue, and one that I highlight on this slide here, which is if I have two adjacent unit tangents and they're parallel to each other, and I take the cross product, what do I get? Somebody, I heard it. No, like say the words, guys. I'm gonna zero. You get zero, right? Because the cross product of parallel stuff is zero. Yeah? So if I want to define the binormal as the cross product of two adjacent tangent vectors, can I do that unambiguously? No. And in fact, this isn't just an issue with discrete curves, it's really an issue with smooth curves as well. That all these definitions that I give you in 3D of curvature break down when I have a straight line, which is kind of irritating because the straight lines are kind of the curves that we like, you know? And so exactly the right question to ask is the Frenet frame the end of the story? And the answer is no. And in fact, I would argue there are a lot of applications where line segments really aren't the right representation, and what we'll see is that all of these things get coupled together in a nice way. There was a paper a couple years ago, it's not a couple years ago anymore, is it? Oh. There's a paper 9 years ago rather, that's a great example of this, and we're not going to have time today to go over it, so I'll roughly describe for you the problem and then we'll start with this next time, which is simulation of shoelaces. So when you're at home, I encourage you to take off your shoes when you take off your snow boots and pull the shoelaces out of them because that's what we do with shoes. And hold one edge of it and start taking the other edge of your shoelace and just twisting it, right? And what you'll see happens, like what we showed you on the screen here, is that you get this really interesting buckling phenomenon. Like right in the middle of the string, you get this interesting little shape that happens. My question for you is, if I think of a curve as a big pile of line segments, is that going to be enough for me to recover this behavior? No, right? Because I have no notion of twist along the curve, right? Essentially a line segment is just one big ambiguous stick, right? It has no notion of what it means for that stick to rotate, right? And so for applications like this, I need a different sort of understanding of discrete curves if I want to replicate cool behavior. Like, so this is a figure from their paper, and you can see that this is a numerical simulation with relatively few pieces on this discrete curve, but because they sort of worked out the right discrete differential geometry of curves, they can get pretty non-trivial behavior. This is one of the really nice themes about this idea of structure preservation, that oftentimes somehow if you take structure from physics and preserve it exactly, you end up with kind of the right behavior when you do your simulation, even in pretty coarse approximation, which is cool. All right. So I think we'll leave the details here for next time, but essentially I'm going to zoom forward a little bit to There's a very cool paper. Oh, the problem is this is one off from this one. That has a kind of a funny title, which is "There's More Than One Way to Frame a Curve." I think it comes from Roger Rabbit. And essentially, what this guy argues is like, okay, we're all like obsessed with the Fourier frame of differential geometry, but it's not the only one. And in fact, there's another one, which now, of course, is known as the Bishop frame, which has to do with the notion called parallel transport, which is going to be very important for us when we talk about surfaces, that is unambiguous along a straight line. Essentially what it says is, I'm just going to define a frame at the very first point of the curve, and then I'm going to drag that frame along the curve with the constraint that one of those three directions is always tangent. Right? And then for the other two directions, I'm going to solve a problem which says make them kind of twist the least. Right? So if I go along a line, I'm just going to keep it constant. Right? And this Bishop frame is going to be useful for applications like this, where really what I'm after is the twist, or in other words, sort of the deviation of my physical system from this most relaxed configuration. Cool? All right. So, well, as I told you at the beginning of this class, these slide decks here are topics rather than lectures. So we'll kind of start in medias res here next time, and go over this nice way of framing curves, and then we'll move on to higher dimensional objects, because that's kind of the end of the story. So hopefully I'll see you guys all on Tuesday. Please start your homework if you haven't already. Have a stellar enough times. Ask questions online, and I'll see you next week. And somebody can hit the camera if you wouldn't mind.